Well, last lecture was a doozy, but now it's going to be a lot easier going because once we understand how to construct a tangent space in this formal way, we can basically reconstruct all of the work we did in the last lectures, the one about what is a tensor. So now that we understand the tangent space as the construction of all the velocities associated with all the curves at a given point, where gamma is a map from the real numbers to the manifold. Once we understand that this is the tangent space and that these objects in here are actually vectors, and we've defined our vector addition because we know that, say, v alpha at p acting on a function, an arbitrary function, plus v beta at p acting on an arbitrary function, we know there exists a sigma, and we actually know how to construct that sigma that acts on the function. The sigma kind of came out of thin air, but that's because somebody else figured out what it was. Somebody studied this problem very hard and came up with sigma. And if you actually sit there and look at sigma very carefully, you kind of realize it's not that hard to put together. You're simply looking for a curve who has this derivative at the point P that essentially is the sum of the derivatives here. It's not too tough to imagine somebody figured that out. Anyway, we proved this, and we did not prove that given a real number A and an element of the tangent space, there is yet another, well, I guess I won't call it sigma this time, I'll call it delta at P, where this relationship is true also, which is our scalar multiplication, right? So this is our vector addition. This is our scalar multiplication. But there is, and you can prove it, and it's very similar. It's actually easier. This is a pretty tough proof. This proof is much easier, and you can prove it. And then this combined with a few other facts, and we have a vector space. And therefore, because every element of a vector space is a vector by definition, we can call these guys vectors. But we've been calling them velocities. And the reason we call them velocities is we were kind of playing with this notion that there's some curve gamma that's plotted in the manifold. Well, it's sort of shown moving through our differential manifold. And in the differential manifold, there are these contours of the function f, which I'm just drawing like contours you might see on a map, but there could be all kinds of crazy things going on. And the notion of the velocity is that we're kind of probing how quickly this curve is sort of moving through changes in this function. And of course, that gives us a sense of in some sense, it gives us an idea of the derivative of this curve relative to this function, whatever that function happens to be. And the function, of course, f is from the manifold to the real numbers, right? That's an important part of this. You have to have that. And so we figured out that we can discover these velocities as long as we have a curve and a function from the real numbers to a function from the manifold to the real numbers. And if we're given those two things, we can kind of create this idea of a velocity. And then what we did is we bundled all the possible curves, and of course it has to be at a point, right? At a point P. And once we bundled all the possible curves that go through the point P, right, every single one that could possibly go through P, right? Including reparameterizations of curves that already are going through point P. That's a good point to make, actually. If I have a point and a curve going through that point, and I call this curve gamma with the parameter t, I could also create another curve with the parameter of 2t, and then I rename 2t, say, x, and I call that gamma of x. This is a different curve than this, right? This is traversed faster. That has a different velocity, right? So these reparameterizations of the same curve count as different curves. So now that we understand this, we have this new object. But what's important to remember about the object is that I can create this thing at every point in the manifold. So once I have this concept in mind, every point in the manifold is going to end up with its own, I guess I'll call it, well, its own tangent space. V gamma q, V, I guess I shouldn't call these gammas, it should be, how about V alpha for this one, V beta P, right? They all have their own tangent space. And the way all these tangent spaces are relevant to the curves that pass through all these points. A single curve could pass through two of the points, but there are curves that pass through one of the points but not the other, right? And this is all now the things we're going to discuss today are how to build a basis for this vector space, because if it's a vector space, it's got to have a basis, so that's an important thing. We're going to talk about the covector space, which those of you who followed along in the other lectures know that the covector space is the set of maps from the vector space, to the real numbers. So we're going to create the covector space, and we're also going to talk about change of chart. Well, let's see, not change of chart, that's not the really good way to put it, but change of coordinate systems. Changing coordinate systems is changing the chart, right? So all of this here only makes sense in a chart U, right? Because remember how we used the chart to create these. The chart has its own chart map. What haven't I used here? Delta to RD, and that chart map was what we used to differentiate these curves, which came from the real numbers, right? So the curves gamma, beta, alpha all came from this real number bin, and this path here is only possible because you can get off of the manifold using the chart U delta in this case, which is an element of the atlas. So now let's first begin by talking about the basis. So I'll define everything first. We are dealing with our manifold, which I will call, well, instead of dealing with a manifold, we're going to deal with just one chart on the manifold. That's important. In order to define a basis, we have to do it relative to a chart. So a basis doesn't even the basis we're going to define only makes sense relative to a chart. So in order to have a basis, we have to pick a chart. So right now, I'm going to call this thing here the chart, right? So that would be U plus its chart mapping, which I'll call gamma. Okay, so this is actually a piece of the manifold, which is going to be x, tx with an atlas, and this is just an element of the atlas. And gamma, of course, takes this thing to some RD. All right, so actually this whole the whole chart region gets mapped over here to gamma of U. Then, well, let's see, we have to have a curve, right? Because we can't really even describe the tangent space, so I'll call that curve alpha, and it's from real numbers. Well, alpha should be shown here, right? And let's do this, right? So alpha is this curve, and the parameter for alpha will be, say, t, right? And then t0 comes to the point P, so that's alpha of t0. And then presumably this curve kind of goes through alpha, and it has a coordinate representative like that. So we know how to write the velocity of such a thing. Oh, well, we need one other thing, right? We need a test function. A test function is some arbitrary function that goes from the manifold to real numbers. Good. And that'll be F. Guess I should have arrows in all of my mappings. Okay. So now we kind of know how to proceed, right? I can say the velocity of the curve alpha at the point P acting on the function f. I know how to write that down. That is just f composed with alpha, right? And then it's the derivative of that. And of course that derivative is going to be with respect to t. And it's going to be taken at the point t0, which is up here, which is which is at the point P. I should write this down, that P equals that. So this is just the definition. This is how we created these vectors, which I can now call them vectors, so I will. We've created these vectors that are living in the tangent space at P, and this particular vector is based on some curve alpha, and it's working on some function f, and this is the basic way of defining that thing. And that the derivative is taken with respect to t should be clear, because alpha, the domain of this thing here, the domain of this thing is the domain of the one on the right, which is alpha, so that domain is the real numbers t. So the only derivative in sight for the domain is t, and the range, of course, is r, because it's the range of the whole composed function is the range of the one on the left. So alpha at t0 is p. So this thing here is evaluated at P, right? So ultimately it's F evaluated at P is what's going on, right? F will ultimately be evaluated, the derivative of this will be evaluated at P, I guess is the way to say it. Anyway, that's our thing. So we've got this chart and we've got this definition. So we use that same trick we used last time, and it is, I hesitate to call it a trick because it sounds sort of crafty or something, but I can always squeeze in there the identity through the inverse of the chart mapping, like this. Oops, T0. And then I can split it into two sort of associatively, right? So I guess what I'll do is I'll take the outside to be braces, just because I don't like putting parentheses on parentheses if I can avoid it. It'll look kind of like this. Operating on T0. And see, I screwed it up already, right? Now I put a brace here, a prime there, operating on T0. Actually, I agreed last time, didn't I, that I would, when I'm operating on something, I will make it a hard edge like that. So that's a good idea. So I should do that. These should all be brackets. So that way I distinguish the argument list from the name of the function. So this is the name of the function in here, and this is the argument list. The name of the function is f composed alpha derivative. Sometimes they say f after alpha derivative operating at the point t0. Okay, so now I've got this thing. Now this is just a pure formal change, right? I started here, nothing really different has happened. But now I will use the chain rule that we discussed in the last lecture. And if I use that chain rule, I end up with partial derivative with respect to the ith element of the list of arguments operating on f gamma inverse, and that is evaluated at gamma alpha evaluated at t0, right? So this is the first part of the chain rule. It's the derivative of this first term with respect to the ith element of its argument list. Remember, its domain is gamma inverse. Well, what's gamma inverse? That's the gamma inverse goes from RD to the manifold. Its domain is RD, so it's looking for a D tuple. So it's the ith is the is the derivative with respect to the ith element of the D tuple of this thing. Where is it being evaluated? Well, it's being evaluated alpha T0 gamma. So it's being evaluated at the representative, the chart representative of the point P. I guess I should put that in there. I should put in here, that's the point P. That is gamma of P, which is also gamma of alpha T0, right? These are the same things, right? And that's the point there. So then, in addition to that, I have to multiply this term to finish up my chain rule. I have to multiply it by the derivative of the inner term. In the composition notation, this would be the inner term. And it's easy. I don't have to use a summation sign or a del sub I, because it's only a function of one variable. So the chain rule is particularly simple here because it's only a function of one variable. So I will multiply it by gamma composed alpha prime, evaluated at T0, like that. And now this is a complication of this guy, right? But the difference between this guy and this guy is that this is relative to a very specific chart, right? We're using the fact that we're dealing with a differentiable manifold here, right? We're using this fact to get to start bringing in this RD, and that's going to allow us to understand the dimensionality of D in the context of all of this, because we jammed that chart in there. And so it sounds like we've complicated it, but what we've done is we've added a convenient device. We've picked a specific chart and written this in a chart-dependent fashion, right? This is all a chart-dependent fashion now. This does not equal this unless gamma is a chart and unless we have a differentiable manifold and all of those things. But if I had a different chart, I could totally write a different expression here. And it wouldn't be equivalent, really. It wouldn't be equal. It would actually be different because these mappings would be totally different. So we'll talk about how to change charts later, but let's figure out what this is actually telling us. So we'll look at it term by term. All right, so let me move it like that. And let's first look at this term here. Why not? Also, there's these little markings here that don't belong. Let me see if I can get rid of them. Oh, shoot. This marking here doesn't belong. For whatever reason, it's there. Okay, so this term, what have we got? We've got gamma composed alpha prime at T0. Well, gamma is a chart, alpha is the curve. So clearly this is the chart representative of the curve, right? This is this line. Gamma composed alpha is that line. The derivative with respect to t is basically asking, it's this line here. So the function gamma composed alpha is going, I'll draw it in red, is going this way, right? That is gamma after alpha. So this is a simple derivative. This is a derivative of a point here with respect to t, right? And it's dependent on this chart. It's dependent on the chart map gamma. So this thing here, because it's the derivative of this thing under one variable, we could actually write this as the curve itself, the derivative of the curve itself. We could say this is alpha dot. Essentially, it's the derivative. We could rewrite this with a tighter notation. We could call it alpha dot. The problem, though, is that alpha dot, which implies the derivative of this with respect to time, again, alpha is a function into the manifold and you can only take derivatives of things that go from Euclidean space to Euclidean space. But maybe we can remember what's going on if we label alpha with the chart that it's part of. So we could label it with gamma, or likewise, if we wanted to, we could label it with the name of the chart U that we're using, the name of the chart region U that we're on, and U is attached to gamma. Or we could put the whole damn chart in there, I guess, right? We could give it a subscript like that. But we could rename it that way. And, oh wait, shoot, this is the ith component, right? This is a component object. Of course, you need to have a component here. This is the ith component, right? Because remember, this is multivariable calculus, right? So the this guy here the range of this is, like I said, it's in RD. It's a D tuple, right? So we're looking for the ith component of that D tuple, right? So this object here is also picks up an ith component. That's how the chain rule works, right? The multivariable chain rule works that way. So now this guy I'm going to rewrite in this red form, right? And that's just a renaming, right? I'm just renaming it for a moment because it's tighter, but we understand what's going on. It is the derivative with respect to the single variable of the curve, the single curve variable of the ith component of the chart representative of the curve, right? So that's why this stuff is not easy. You got to kind of keep track. You got to keep these pictures really clearly in mind to get and understand fully what's going on. But we are going to build some symbols that kind of contain all the logic, and eventually you can sort of forget about the manifold structure. But if you don't understand this manifold structure to begin with, if you don't understand this and how these charts are written and where these derivatives are taken, and you're just introduced these kinds of things, it's all sort of a mystery, or I felt it was, which is one of the reasons I'm kind of doing this lecture is I'm trying to get to the core of what these things meant, and to do it, you've really got to walk through this subject of manifolds. So we've understood what that is, and now we will look at this part, right? We'll look at this part. And so, what is this thing? Well, we'll start, of course, with the function itself. It's the inverse, this is an interesting thing, it's the inverse of the chart mapping composed with the function. So what would that be? Well, here's gamma, the inverse of gamma, so I take a point in RD, go back to the manifold, and then I get a real number, right? So, and then it's the ith component of that. Well, then I take that, and I take the derivative with respect to the ith component of its argument list. Well, what's its argument list? Well, alpha of T0 is P, and this is the chart representative of the point P. So, all right, so let me simplify that a little bit. I can write this down as gamma of P, right? So whatever that is, it's gamma of P. So right now I've simplified it a little bit. So now I have the ith, I have the derivative of this the inverse chart of basically the derivative of the function under the inverse chart. The derivative with respect to the ith entry in this thing. Well, this thing, of course, is a d-tuple, right? So you know that this thing is going to be something like x1, x2, dot, 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 xd. So the ith derivative is going to be the derivative of this function with respect to one of these variables with the others held constant. That's what a partial derivative is. And it's this function composed with this inverse mapping. So here's the function, the inverse mapping. So basically I'm taking a point, in particular the point P. Well, first I take the derivative of this function, right? So this, I guess I could write this in blue, right? This function goes like this, right? It's inverse gamma composed with f, right? So that's the function here. So I take that, I construct that function, which isn't hard. I just compose my map gamma with my function f, and these are arbitrary things. We know they exist, by the way, because everything's, well, this is continuous, and so this function will have a sort of a continuous argument. So it goes like this. I take that derivative with respect to just one of the coordinates up here in RD, and then I evaluate it at the point P. So that's what this thing here is saying. And so I'm going to write some crafty, smooth notation for that too. And that's the notation that we very frequently see. First of all, this since gamma p is this, I can actually simplify this derivative a little bit, or not simplify, but make it clearer. I can go d by dxi of f composed with gamma inverse, like that, evaluated at gamma p. So that's one thing I can do. Let me make it clear. Evaluated at, so now I've simplified that a lot. I can make my evaluation look a little bit cleaner by writing it d by dxi of f gamma inverse evaluated at, I could just say p, right? Well, I could say gamma p, right? Because it is evaluated at gamma p. But now I can kind of say, all right, we know that this is all relative to some chart, right? So let's just forget the gammas, and let's just write this as d dxi of f evaluated at p. And I kind of drop the charts, right? And I need to sort of know that this is relative to a chart. But how do I know that I'm talking about this thing relative to the chart u gamma? Well, the only thing that hints at it here is these x's. And I've defined u gamma, I've defined u of some point p to equal, let me move this over again, to equal x1 of p, x2 of p, dot, 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 to xd of p. So presumably some other chart, phi of p, would have to be something like y1 of p, y2 of p, dot, 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 yd of p. And because of that, right, the y's would be associated with the chart phi, the x's would be associated with the chart gamma. So here I see the x's, I say it's associated with the chart gamma through this definition. So this object here now becomes the notation for this side, where I track the fact that it's associated with the chart gamma with these x's through this definition. There's an alternative way of doing it notation-wise where I define the chart as u x, where x is the mapping, right? And then it saves me a little trouble because I say x of p equals x1 of p dot 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 xd of p, right? And I could say a different chart or a different chart mapping. I could say v of y, and then that would be y of p would equal y1 of p dot 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 to y d of p, right? And now using this form, I've named the mapping the same as the coordinate functions, and that's actually done a lot. In fact, I probably should have done it here just for simplicity, but I started with this sort of gamma as the mapping, although sometimes I've used gamma for the symbol for the curve, so I've been a little bit inconsistent, I suppose, but within the scope of each part of my talk, I've been consistent. But this is probably a very common way of going. But here, the problem I don't like is that it's confusing. You can easily confuse x with a coordinate instead of with a whole mapping, a multidimensional mapping. So it's got that weakness. But anyway, this now becomes a symbol for this. And it's a little bit dangerous because you're losing the mapping here. So you don't realize that this thing here, the derivative you're taking, is really the derivative of f under this you're taking f under this inverse mapping. So it's going from RD to R, which is of course what you need because you're going to take it with the derivative. That's the only way you can take the derivative. And likewise, it says it at the point P, but you're actually evaluating this thing in RD, which is here, which is in the chart representative of P. So you don't, so you kind of lose a little bit there, but turns out you can operate with this without thinking about that. It turns out this is very efficient notation. And so now I can rewrite this whole thing like this. I guess I'll do it in green, right? I can now rewrite it as alpha dot I, and I'll just put the chart down there, times df dxi evaluated at P, which we can separate the f from that, and we can go alpha dot I gamma d dxi evaluated at P on the function f, right? And this is our basic archetype for how to write down a vector v gamma at P operating on f. And the reason this is important is you see you have these things here, which are derivatives evaluated at a point, right? This is a derivative here evaluated at a point. So these are numbers, right? So these guys are numbers, and these guys are operators that operate on an arbitrary function f. And they do it in exactly the way you would expect. F is a function of x through, x1 through x2 through x3. So you can take the derivative of f with respect to these once you understand that f is really f composed with gamma inverse. But we're just now, so you're almost relabeling this thing, where this means this, right? Whenever you see this, you kind of want to substitute this in your head. And that actually means you know too much. You make it more complicated. But once you understand that f is, in this context, is a function of the x's through the fact that it's composed with gamma inverse, then you're okay. You know that f is a function of x, and you can take that derivative and then you can evaluate it at the point P, although you're actually evaluating it at the point gamma P, right? Because that's the only way this makes any sense. But these guys here now, they're the things that we are going to call the basis of the tangent space. So this object, d by dxi, evaluated at the point P, that's the basis of the tangent space. Basis of the tangent space. And you can see, it's got the same form, right? It's got the form of a real number with an Einstein sum and a basis, right? So this actually looks like E I xi, right? Where x is some set of components, right? So these are the components here, and this is the basis vectors. And then the basis vectors acts as differential operators on functions. And that's exactly the construction I offered up in the other set of lectures about what is a tensor. But this is valid at any given point, and that's really important. The point is clear. The fact that it's a mapping is understood through the fact that you've got these coordinate functions here, or these coordinates in there, and so that implies that there's a mapping involved, and so it implies that it's all stuck on one chart. Which brings us to our next point. This is only valid for one chart. So the idea is that once you have this gamma, you've established a coordinate system, right? We now know how gamma is related to coordinate systems, right? So there's some coordinate system here in RD that's projected back onto the manifold, but the coordinate system exists here in RD. once I set up that coordinate system through gamma, the relationship between the manifold and that coordinate systems through gamma, now the basis of this tangent space at P, that basis is completely dependent on that coordinate system through the way the functions are dependent on the coordinate system. And these functions here, f, are really these things, right? So the functions get tied to the coordinate system through the reality of what this symbol means over here. The functions get tied to the coordinate system through this gamma inverse. And once that happens, now you can take the derivatives with respect to that coordinate system. But it all depends on gamma and on gamma's coordinate functions. So this basis is completely tied to the coordinate system, which brings up the question, well, how do we change coordinate systems? Because we know we can change bases. How do we do it in this context? And it's actually now these proofs are kind of simple, but oops. But if I start with two different charts, right, and I'll use sort of the same thing that I've always used. I have a chart U and a chart V, and U's chart has the mapping gamma, and V's chart has the mapping phi, right? They both go to RD. Now, of course, I'm only dealing with charts, but out here in the wider world is the full-on manifold X, TX with an atlas, and of course these two charts are members of the atlas. U and V are elements of the atlas of this differential manifold. So once I have this in mind, if I have a point P here, right, I have curves, right? The curve comes from the real numbers, and I guess we're calling that curve alpha. So alpha runs through here, and the alpha's in the manifold. The locus of points in the manifold is the same no matter what chart you're in. The problem, of course, is that under U, you end up with this curve, and under V, or through the charting phi, you end up with this curve. And those are different. I mean, those are in different spaces, and they could be shaped totally differently. And then, likewise, your function goes from the manifold to the real numbers. That's the function f. And so these guys here, the guys that go like this, which in this case would be gamma inverse composed with f, and like this, which would be phi inverse composed with f, those guys are different also, right? So so now how do we reconcile all of this? Well, I'm going to start with rewriting the definition of my vector. So now I can call a vector, or a velocity vector, I can call it, say, x. And x, when I break it down into components, it's going to have a component part, xi, and it's going to have this basis part, dxi, evaluated at p, like that. And in this case, my xi will be related to the gammas. Again, I'm writing this issue where gamma of some point is equal to x1 of the point dot 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 to xd of the point. And phi, I'll define this way. Phi of p equals y1 to yd. So these are the coordinate functions here. xi of p and yi of p. Those are the coordinate functions. So so right now the vector that I'm just naming it, I've got the basis, and this thing, this is where all the information about that curve was, right? If I really deconstructed that, I would have ended up with, you know, some kind of curve with a dot I based on some chart, right? But I don't need that anymore. I'm just proposing the vector exists, and and I'm just writing down those components as real numbers, right? I'm just assuming that these real numbers are there, and it's this Einstein sum. So I take, yeah, that's a good point. This is an Einstein sum, right? So this is going to be x1 d by dx1 plus dot 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 xd by d by dxd, right? So that is an Einstein sum. So I write that down. But it's also true, so the only possible ambiguity here is, although this here is tied to gamma, to this chart, through the fact that I have these x's here, right? And the x's are the component functions. I don't really have anything in here to indicate that this component is tied to gamma. So in order to do that, I might have to throw down a little gamma there, like that. But the reason that's important is because I also want to write xi, say with respect in the phi coordinate system, right? That's going to equal dyi, also evaluated at p, right? That's easy enough. So this is two ways of writing the same vector, right? The same vector in the space, two different ways of writing it, and the difference is the basis, and the basis are derived because you have two different chart mappings for this curve. So these are two different coordinate systems is what's going on, right? So now my question is what's the relationship here? Because we're always interested in relativity about how these coordinate systems change. So what do? Well, we have to kind of step back to our core definitions always, and let me erase this part. And I'm going to rewrite this term the way it was meant to be, right? This is meant to be x gamma of I with the derivative with respect to the ith entry. Oh, and I'm going to throw in, well, let me not do it yet. With respect to the ith entry of an empty slot, right? This empty slot here is this missing slot here, composed with the mapping, the inverse mapping, right? The inverse mapping gamma, and it's evaluated at gamma of p. Right? That's what this means, right? That's that's the definition of this symbol, right? This p flows from the gamma of p, the chart representative of p. This gamma inverse is related to the chart for which these are the coordinate functions, and this missing slot is the missing slot here, which would normally take an f, right? I would act on this with some arbitrary function, and that would land right there. So let's actually do that, right? Let's fill in that spot. So what I'm going to now speculate is, well, we're going to talk about x acting on a function f, which is going to be x gamma I di f gamma inverse acting at gamma of p, like that. And now I'm going to just talk about the change of chart. I'm going to slip in phi and phi inverse. X gamma I del I f, where will I put it? I put phi inverse here, composed with phi, which is just the identity, so we can do that, gamma inverse, and it's still evaluated at gamma of p, like that. And then I do my association, right? I'm going to associate these two as separate functions. So I will write this as x gamma I, derivative with respect to the ith entry of this d-tuple of f compose phi inverse, compose phi, compose gamma inverse, with this derivative, and then that's evaluated at gamma p, like that. And then I use the chain rule, the multivariable calculus chain rule. So I've reset the screen a little bit before we take this multivariable calculus derivative. because it's kind of tricky and I wanted to get everything on the screen. I tried it once and it didn't work out very well, so I'm redoing it. So this, of course, is all of our architecture kind of squeezed down here, and here we are waiting to take the multivariable calculus derivative. So that next step to do that is we just sort of break it down very slowly. X gamma of I. Now this this derivative with respect to the ith entry, is with respect to this ith entry. So this I is going to land over here on this function. So we do it like di phi acting on gamma inverse acting on gamma of p, like that, and then that object is multiplied by, let's see, do we need the jth component of that? Hold on. Yeah, right, and then this is the jth component of that thing, because we need that to tie to the derivative with respect to the jth entry of the outer function, which is f composed with phi inverse, and f composed with phi inverse has to act on the inner function evaluated at this point here at the end. So that's going to be phi composed with gamma inverse at gamma of p, like that. So let's see if this makes sense, right? We have the jth component here is summed over the jth entry derivative here. What's this thing? Well, this is gamma p, that's the chart representative of p, pulled back to the manifold through gamma inverse, and now it's phi of p in the manifold, so this is the chart representative of p in the phi chart. So I can write that as phi of p. And then what's this? This is just this is the definition of our simplified notation that we had here, but it's in terms of the y component, the y charts, because it's got the phi there, and we've defined phi in terms of the y charts. So I can write that as df dy j evaluated at gamma p, right? So that whole thing can be put together to be df dyj, or I can even take it a step further and get rid of the f, right? df dyj evaluated at p using our full-on notation operating on f, right? So this whole thing here has become that there. And what about this side here? What about this stuff? Well, that's the components. That's not going to change. This is actually a transition function. It's the jth component of a transition function, the derivative of the transition function with respect to the chart representative of p. We know the derivatives exist because it's a differentiable manifold, so we know that transitions from RD to RD, those transition functions are differentiable and they're smooth. So we don't have to worry about the existence of that derivative, and we have the jth component of that thing. So the jth component is going to select the y component out of this ordered d-tuple, and the definition of this is a function like any others, but it's got the yth component. So this is phi, the jth component of phi, which is going to be one of these y's, and that is going to be simply dyj dxi based on the definition of our understanding of our notation, right? It's the way this notation works. The chart representative inverse, we take its component function and put that in this denominator of this symbol, and that's what this is. This is dyj dxi, and it's evaluated at P, and that comes from the fact that it's evaluated here. And again, we're kind of getting rid of these gammas a little bit, but that's how the symbol works. And this thing here replaces all of that. So this can be written this way, and then this just comes straight on down as x gamma I. So in the end, when I put this all together, I get x gamma I dyj dx I, evaluated at p, times d by dyj, evaluated at p, acting on the function f. And ultimately, the whole point of all this is right here, right? This I just rewrite as x phi of I. And now I have my rule that translates the x, because the reason it's x phi of I is because this is the basis in the phi chart, right? This is the phi chart's basis. Just like this is the x chart's basis, this is the phi chart's basis. Where if I was a little bit neater, you would see the phi right there, right? So now my rule is very simple. X on the phi chart at I equals x on the, I guess we call it the gamma chart, times these solvable derivatives, the derivatives of the component functions evaluated at p. And these are known functions, right? These are known because we know how these charts work, right? The charts are very unambiguously established, so the derivatives of these coordinate functions relative to each other make sense. Now, the reason we have to understand that this is up here, right? The symbol is, the way we understand this symbol is through the sort of the simplified notion that y, the new coordinate yj, is a function of the old coordinate xi, and the old coordinates xi are functions of these, well, the gamma coordinates, well, in this case, the way I should say it is the phi coordinates are functions of the gamma coordinates, and this way I would say the gamma coordinates are functions of the phi coordinates, right? Like that. And because of that, I can take these derivatives here and plug in the representative of p, which would actually be, in this case, it's evaluated at the point p, so these would be evaluated at gamma p, right? I take the value of gamma p and put it in there, and that will give me a number, and this will end up being real numbers. And this is a bunch of real numbers multiplied by real numbers through an Einstein sum. Are my indices correct here? Wait a minute. I'm summing over I. This has to be a j, right? This has to be a j, because these i's are Einstein summed. But this whole process is how we get this basis change for the components. And we've kind of worked through it, but it all starts with the core definition of how these symbols work, jamming in these new charts. And we understand coordinate changes now on a manifold are changing from one chart, the U chart, the U gamma chart, to the V phi chart. And they each establish a coordinate system on the manifold, and ultimately we can recover the classic general relativity transformation rules through understanding how it's all about these charts. All right. So that is our coordinate transformation rule through manifolds, and we probably won't talk about it anymore. We'll go back to in what is a tensor, the sort of the standard system we were using there, but now we kind of see where it came from. Okay, so what did we cover today? We covered basically we covered basis vectors. We covered basis vectors for the tangent space. And the way we define these basis vectors are derivatives, these differential operators with respect to the chart functions evaluated at the point P in the tangent space, which is really defined by the ith entry of the derivative of this blank times the inverse chart function, right? That evaluated at the chart representative of P, right? This is the definition, right? This is what this symbol means, right? We always have to kind of remember that. So those are the basis vectors, and then we discovered that we discovered how to change charts, and then we now know that changing charts corresponds to the general relativity notion of a general coordinate change. It's sort of the same thing, and it had to do with this del y j d x I and the components changing, and so with the chart here, with the chart indicated here, and all at P. Again, everything is at one point P. Very, very important. And this is what we got through today. I was going to do cotangent spaces today, but there's no way. It's already about an hour-long lecture. So next time we do cotangent spaces.